Good afternoon, YouTubers. Here we are. We're going to be talking about how to expand the Arduino Uno memory using static RAM. And certainly you can use SD card, but in this project, my idea is to expand these like if this were like a microcontroller with the capability to address many lines in a kind of a, I would say, large memory bank, like would be a 32K times 8 bits static RAM. So that's the idea. With that said, let me put this on. See, all right, there we go. So if you are familiar with Arduino Uno, the Arduino Uno has kind of a extremely cheap. That will be something that some people might be important. It is important, and my project basically will boils down to at about $10 on parts. Static RAM would be about $4 plus several other chips that we need. Shouldn't go above $10. The whole thing. That's without the Arduino, obviously. But Arduino are cheap as well. Might be like $2 or $3 as well. So it's not a big deal. Now, the important part here is that Arduino has about 14 pins, and from those 14 pins, basically, there's 2 pins very important, which is pin 0 and 1, that I would not use them for my project. They are for communication, and they're very important for troubleshooting and doing many other things. So I will not use those ones. So from those 14 pins, actually, we only have 12 available to do my project. And obviously, I don't want to use all of them for the RAM memory. That's not good. So this is a little bit more details of what those pins are. And as I was saying, the transmitter pin and the receiving pin, which are 1 and 0, I will not use those ones. So I will have the remaining other pins just to do the communication between the Arduino and the static RAM. So that's basically the idea on the project. This is a 32K by A static RAM, which is basically the one that I will be using. And as you can see, I mean, we have here about 15 pins. If we want to address the 32K bank memory, then we need at least 15 pins to address all that amount of memory. But we also need 3 more pins for controlling the chip. In this case will be like either chip select or chip enable, typically called chip enable. Oops, sorry for that. Chip enable, write enable, and output enable, depending on whether you are reading or writing. And then you have the other 8 pins for the bus line. So here's the address line, here's the bus line. If you add all that together, you will quickly realize that will be way beyond the number of pins that you have in an Arduino Uno to work on this. So what's the plan? The plan is to use a concept by many others before me, and I kind of like this one from Bellamy. I put his address, his URL right there. You can take a look at his information. And the nice thing is that, as you can see, his project was for controlling 24 LEDs, and depending of the information that he wants, he can control any of them, individually, and that's very important. So with 3 lines, basically you can control 24 output pins, and the lines are data, the latching, which is basically the buffering out the information that is on this chip register, because the concept is based on the 595 chip register and the clock. Every time you clock these, I mean, the three of them will kind of shift the information around. So, but the data and the clock will go kind of together. And then when you have all the information within the register of the 595, then you hit the latch, and then you get the information out, and you will either, you know, turn on or turn off based on the data that you input into the unit. So this is kind of cool, because basically with 3 lines, you are controlling about 24 output lines. That's a lot of lines. I mean, you are giving now the Arduino the capacity, or now the Arduino is capable to control about 24 lines, and even more. I mean, you can, these are in series, I mean, and so forth. So you got 8 bits here, plus another 8 bits here, plus another 8 bits here. So you want to add another one of these, then you keep adding, and you can see by doing so that you somehow resolve the issue about the address line here. So you can really, with 3 lines from the Arduino, you can start to control many output lines which are required for the RAM. All right. And let me see if I can see in the next slide. Oh yeah, I can see it here from the next slide. On this one, I'm saying basically, let's say, or I entertain the fact that I'm going to be using only two 595. So from this total of 16 lines, 3 of those lines will be used for this part here, for the controlling the RAM status, like for example, chip enabled, write enabled, output enabled. So I really have, from those 16 lines, because I'm using only 2 chips, 595, from those 16 lines, 3 will be dedicated for this part here, for controlling the status of the RAM. So the other 13 lines, which is this part here, the other 13 line will be able to control about the 8,191, and that's about 8Ks. So I will not be using the whole 32, because I'm only using 2 595. I mean, this is sort of, I don't want to go to a third one without testing many things that I want to test. Like for example, yes, that this kind of a scheme work for either reading or writing, you know, at least 8Ks of this 32, and that the speed of the Arduino in doing like the part of writing and reading is fast enough that as for my project, my project is just it's a solar or a photovoltaic project in where I want to construct a data logger to save voltage, current, etc., just to give me a lot of information about what's happening on a daily basis on a solar project that I'm working on. All right, so that's the idea. So this part here, again, solved the issue with the address line. How about the output line? But the output line, I'm planning to use the actual, the Arduino directly. So there's techniques that you can convert, either read these lines from a parallel to serial converter and perhaps use 3 lines. But at this point, I believe that the solution that I have already will work. That a good hint that it will work the way I'm planned, is planned. So again, depending on the number of pins that you have here is the amount of memory that you can read. Like for example, as I said, you have 13 pins, you can read 8Ks. You have 14 pins, then you can read about 16K. You have 15 pins, then you can read 32Ks, 16. So you add 3 of these, the way it is right here, that's 24 pins. less 3 pins for control, that's 21 pins. 21 pins, we can read about 2 meg of information. That's a lot. I'm not sure how fast can you read them or write them. So I would not, dare to go that deep into it. I will let you know how system work, at least using only 13 pins for the address and 3 pins for the other part, which is the controlling of the RAM. Again, as I was saying, the output part, you can either convert this output, which is in parallel, to serial using the 165. And there's a good video by Kevin Darren also in YouTube that you can take a look at it. And so something that can reduce the number of pins required from the Arduino on this type of project. But for me, I will only use this part here, only those 2 chips, 2595 for the address line. And within these 2 chips, the control line will be addressing this. So basically it boils down to only 3 lines here and a line here. That's about 11 pins, and that's all what I need. And so that will work. That will work definitely. So keep going. So here's the idea: 3 pins for the 595. See, yeah, this is for controlling these 2 guys here. I need 3 pins from the Arduino. It says 3 pins for the static RAM. Well, this is for controlling the static RAM. You want to use 3 pins from the Arduino separately. But I changed a little bit the way I want to do this, and these 3 pins also belongs to this guy here, and that excuse me. And with that said, basically 13 pins for lines and 3 coming out of here for controlling, and all that will be done with only 3 pins from the Arduino. So this is gone. 8 pins for data. Yes, this will stay, and that will give you the 11 pins required from the Arduino. 2 pins from analog is not required any longer. So we are in good shape there. Keep going. If you happen, I will, send you to see my first video on how to use the 595, and so I will not discuss this much deep into it. Basically, these are the 3 lines that we use to control the 595, how it shifts information, and so forth. But you can take a look at the video number 1 and video number 2. Both of those videos are addressing the issue is how to use the 74595 GIF register. You can definitely take a look at those videos. This is the first video, a circuit to test the 74595. This was done on Tinkercad simulator. That's the first video. As you can see, here is the 595, and there's some extra chips just to control the counting. It's very easy to, when you do this manually, where you are, whether you are in bit number 3 or bit number 4, it's kind of hard. So you have to have some feedback of what you're doing, and that's why you use this kind of a setup. Again, that was done on Tinkercad, and that's it's a nice simulator to do this kind of a small project, and that was my first video. Now, the second video is a little bit more complicated. I add the second 595 to ensure that I can, address all these bits of information as shown here. This is the most significant bits, and this is the less significant bits. And this is just for the status counting. I need to count to 16 bits, and this is the last one. When this light up, I know that I'm in the 16 bit, so I kind of push the data, pressing this push button, press the data, and whatever information I clock in will be shown right here with those LEDs. And information, I have it here, so you need to follow something written so you don't get lost on the process. All right, that's video number 2. Woo, now this is video number 3. Actually, I'm not sure if I want to present this on this video because it's pretty much ready and I can jump into it, but it will take a while to explain a few things there. I'd rather explain as well as possible how to properly use the static RAM, because the way you understand this, everything else here is pretty much straightforward. It's understanding how these logic lines works and what is this NAND gate are doing here. Very important. One of the things when I start this project is that what happened when you turn on the Arduino for the first time. And you want to be 100% sure that the RAM or the static RAM chip is on a high impedance level, you know, or a high impedance state. So the data, if it has data, is not corrupted. And so that's what I have this pull-up resistor right here, pushing this up. But not only that, when this system starts for the first time, this NAND gate convert all this control line to a high state. So that's to ensure that when you do a power up, your data is not corrupted within the static RAM. Okay, so I mean, here you see the 2 chips, the two 595. I have an extra here for 4040, but this is just for a binary counter. Otherwise, now if you don't pay attention of the clock or what else you're doing here, this will not work. I mean, you are doing this by hand. You are inputting data by hand, clocking the information in, buffering that information out. So it's kind of tricky. The next thing is, what is all this? Well, this is the information that I want to be writing into the static RAM, or either reading from the static RAM. This is kind of neat. This is done in, I forgot to say that this is done on Proteus. I kind of practiced for a while using Tinkercad, but when I finally got to this project, the Tinkercad did not have the static RAM, and Proteus, it does. So I downloaded, and within a couple hours, I was using it, to do very complicated stuff. And this is not very complicated. It's just more ensure that all lines are connected properly, because that's one of the problems that I had, particularly with some of these push button, that they were kind of a LAN in, but they were not really connected. So you want to be sure that they are properly connected. And the other thing that I like about Proteus is that you don't need a bunch of LEDs. I mean, having LED here and there is just kind of crowd the whole, the whole desktop here. I don't like it. And the nice thing about Proteus is that I have that feedback right on. Like, for example, anything that is blue here is off. Anything that is in the red state is on. If it's sort of like gray out, it's in a high impedance state, which is also will let you know that there's something happened with that particular pin. So very quickly you can troubleshoot a lot of what's going on, with your simulation when problems show up, and they will show up. So again, let's keep going. This will be part, perhaps, of another video about how to do this simulation. But the first thing is you have to understand how to use the static RAM. We have to understand this, otherwise this will not make sense whatsoever. I'm using this 32K RAM memory, or static RAM memory. It's low power CMOS static random access memory, organized as a 32,768 word by 8 bits. Good. and so forth. More information. Oh, here is a good one. 55 nanoseconds. Watch for that one. 55 nanoseconds. I would say from where I come from, that's very fast, extremely fast. So here's a little bit more of description of the block diagram of your static RAM memory. Again, the controlling line, chip enable, write enable, output enable. They are what they call it active low. Here they don't have the top line, kind of confusing there, but they are active low. Watch for that one. Very important that you understand that. And well, nothing else, the address line and data lines, no big deal. Here's how the chip looks like. I'm planning to use this type of configuration. Okay, no big deal there. All right, here is a truth table. This is important. When the chip enable is in the high state, it don't care about the output enable or write enable. You are in the high impedance state, no big deal. When the chip enable is low, then it's watching for something here. That's important. Now, if this output enable is high and the write enable is high, again, high state, impedance, no big deal. When you want to read, you have to have chip enable and output enable low, write enable high. What happened when you want to write? When you want to write, this low, and this I don't care. Well, actually, you want to be careful. I mean, when you push data in, you want to know in what status that data is in, just to avoid problem later on and mistakes. So if I'm writing data into my RAM, this will be high, period. And so this will be 0, 1, 0. And that's how I work this out. I don't want to mess with this, with the truth table. Now, read cycle. I checked the numbers, yeah, 55, good. I know that, I mean, I knew that from the beginning. And 55 second minimum, 55 nanoseconds, sorry for that. Well, I tell you the truth. I check this information, but I don't care. Bottom line, I don't care. This is way too fast either to read or to write. In other words, the Arduino is in the order of microseconds, and compared with nanoseconds, that's a difference of about 1,000. So in other words, I would not worry about much about this, and I didn't. So keep going. I did check this, and that's important because, and I'm using a recycle that makes sense to me, and that is easy to implement. If I want to read, I push data out of the address from the 595 chips. I load the chip enable and the output enable. See, these two, you will say that there's a little bit of a difference between chip enable and output enable. The truth is that it's none. Basically, when you drop these two, this will be so fast that you will be reading that information in no time. So chip enable, output enable, you drop it, chip enable, output enable, and you will be reading. Now the write enable is on a 1, meaning it's a high state because you want to read information. That's how this goes. So that's only the information on those 3 control lines from the 595 need to have a 0, a 1, and 0. Be careful there. We want to talk about this a little bit more. For writing, I need that this line here for writing, sorry, this part, be 0, 0, 1. Again, there's 2 ways to do this. First, put the address. Second, write enable, drive that line to low. And then third, chip enable low, and then you can write the data. You will be writing data into the RAM memory. I have implemented both. I mean, implemented the strategy in where I go write enable first, chip enable later, and the data will be written into the memory. Or what I'm doing lately is chip enable and write enable simultaneously. What is important is that you have right at the control circuit for the RAM, the 0, 0, 1, and you will be writing data into the RAM memory. That's how it goes. Before we finish this video, I need to explain a little bit more of this here. Be careful, extra careful. Let's see if I can move the next page. And here what I was saying. The lines required at the RAM memory right here are coming from these NAND gates to ensure that when I power up the Arduino, the RAM memory are in a high impedance state. So that means the material, I mean the line coming from the 595, if I wanna read, I mean the read cycle, I need a 101 coming from the 595, and those will be converted to 010, which is required for reading. The same is true for writing cycle. Again, 110, and that particular order, chip enable, write enable, output enable, because basically the 11 will be converted to a low and a 1. Output enable, in this case, is high, and the chip enable and write enable are low, meaning that I'm going to be writing into the RAM. And that's very important. You know what? If for any reason this output enable go to the high state, although the truth table didn't put it that way, it said it didn't care. If these two lines are down, it would not care about this. There's some RAM memory that do cares. And that's why I kind of stick to what had worked before and, you know, keep me straight. I'm not goofing out the logic behind the static RAM. So let's see what's next. Basically, that drive me right here and to my project, how to add a static RAM. I mean, this is going to be an 8K/8 to an Arduino Uno, and very important here. Like for example, this is an example of my simulation that I will do this by hand, you know, manually. You start with this 0, 1, 0, and then you move to 0, 1, 1. This is what I was telling you, that first of all, you want to drop the bright, this 0, 0 become ones when they go through the NAND gates, but the 1 will become a 0. So that means the write enable will be ready. So I'm going, this is the how you write into the static RAM memory, but you know, one step. The second step, this is the first step. The second step, then you drop the chip enable. So now you have the output enable, which is the most significant bit, which is this one here, will be in the high state, like with this red as shown here. But these two lines will drop. And that means that whatever I have put here, the information that I want to kind of set into the RAM memory, it will be set. Like for example, I want to set a 1, 1, 1, 1, 0, 0, 0, 0, meaning the 1, 1, 1. This for the most significant bits. So I have to do that with these bits here, right? And so the address, how about the address? Well, this is the information of the address. Like for example, this one is address number A. So you want to push this information into address number A, and at the end, you put 0, 0, 0 here. That will go right through this one, and that will drive the static RAM to a high impedance level. Reading information is more straightforward. You just show up here on your control line a 0, 1, 1, 0, meaning the most significant bit, and that's 0. Let's see if I'm right. 0 output enable. Yeah. So let's see if I'm right. Hold for 1 second there. Let me see. I'm thinking. Let me think about it. So, oh, I see. Now, sorry for that. This is not for reading. This is if you want to write this data into the static RAM. And again, this is sort of like the short form of writing. Instead of going from 0, 1, 0, 0, 1, 1, the shortest route would be just put a 0, 1, 1 and write the information. And this is the information. You want to have this data 1, 0, 1, 0, 1, 0, 1, 0, and you want to write that into address number 9. Then you send the address. This is address number 9. This is 2 to the 1. Actually 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, that's 8, and 1, that's 9, address number 9. So basically this example is adding information to address number 8 and address number 9. That's basically what this do. This part here is the sort of two-step of writing information, and this is a single step. Now, reading is simple. Reading, you just press 101 as a control line. You just check this one as they go through the NAND gate. That one will drop to 0. The output enable is high. Now the write enable the output enable is low. This will be high, and this will be low, meaning that you are reading information. One important thing, not at the simulator level, but perhaps you are doing this, in an actual breadboard or so forth. You want to be sure that when you are reading, you have all of this here, all these push button in the off state, the way that they are shown here. So whatever information is here, written within the RAM, it will be show up properly. Like for example, if I want to read what is on memory A, should show up this number, and you will see it right here the way that this bit either light on or light off. If I want to read, like for example, what is written in memory 9, so that's what I would do, 101 as my control line, and then I check this. This last step, which is also here, is only there just to ensure that I can do other things, and I put the RAM memory into a high impedance level, and that will not corrupt whatever information is right there. This video has been, it's long enough already that I don't want to do the simulation as part of this video, because it will take another 10 or so minutes to do that. So I'd rather stop here, and thank you for your attention. I'll wait for the next video that will show up shortly.